Okay, welcome to this screencast. We've got section 5.3, solving trig equations, part 2. This is example 6, squaring and converting. As I was mentioning in the first section, you know, they've got these little headings in the textbook, but you're going to need to be able to recognize the strategies and put them into play. The study tip there says that what we're going to do is square each side of the equation, and because the squares of sine and cosine are related, the same is true for secants with tangents and cosecants and cotangents. So if you come across an equation, this is just one example. We've got cos and sine in the same equation, but given that they're not squared, we're stuck. That said, if you square the equation, then what follows is what I just said in that study tip. Okay, this is similar to, but obviously very different from the strategy that you would have learned in Algebra 2 if you are given what's known as a radical equation, or an equation that has a radical function in it. Whether it's square root equation, you know, if you had an expression under a square root, then you'd square both sides, and then you get rid of, so to speak, the square root. This is a completely different reason to use that, but what we know is if I square both sides and I can get into cos squareds and sine squareds, then I should be able to manipulate my equation and do some replacing. Okay, so that is that's the preamble. Example 6, style equation. Again, you're going to have to recognize these ones and use the appropriate strategy. Okay, so give that a shot, and then just to optimize screencast time, I'll put the solution up there and I can talk over the solution. Okay, lots to talk through with this one. I'll give it a go to keep it concise. The first step was spoken about at the beginning, and then that's about it. You had to think of the rest of the strategy and all of the other conceptual leaps here. First of all, the squaring, don't forget to do it correctly. When you square cosine x plus 1, you are expanding a perfect square binomial, and you're going to end up with a trinomial. Don't forget that middle term. That will go very badly if you do forget that. Okay, so it does end up in that trinomial. So this is cos squared x plus 2 times cosine x plus 1. Sorry, that's the top row. So you would have expanded that, and then you still find yourself in a situation, thinking back to the previous examples, where you have two different functions in there. There's a couple of different ways you could go about this. You might try to bring together cos squared and sine squared, but you notice that's not necessarily going to happen very easily. Instead, what I've done here is package that together with a replacement. So sine squared x can just be straight up replaced with 1 minus cos squared x. That's the easiest way to think about this. I suppose there is another strategy where you replace that 1 with cos squared x plus sine squared x, and you'll get to the same place. Definitely then there's a conceptual leap that you take to go into solving that. Okay, so the idea is collect like terms, so just like example 1 or whatever that one was in the previous, collect like terms, and you get to a spot where you've got 2 cosine squared x plus 2 cosine x equals to 0. Bringing everything to one side and setting it equal to 0 is a bona fide quadratic equation solving technique, and so if you did that, of course, that's another conceptual leap in this question. And then putting into place factoring and setting us equal to 0 using that zero product property. Yet another one. Each step of the way here, actually, you're putting in 2 to 3 months worth of algebra learning that you've done over your high school career. So then now it comes down to the actual trigonometry part. This is a challenging question in case you hadn't noticed. Each of those 4 lines requires you to do something not only correct but also strategically efficient. So yeah, sorry, I was going to be concise. Now to the trig part, and then actually to the extraneous solution part because we squared. The trig part leads us into 2 mini equations as we've seen in other cases. 2 cosine x equals 0. You need to be in a situation with your trigonometry that when you see the cosine function and you see either zeros or ones, you should be thinking about quadrantal angles. I don't have enough space on here, but you would have the main ordered pairs there, 1, 0, 0, 1, negative 1, 0, and 0, negative 1 drawn out. Again, that has to come to your mind when we have a combination of cos and 0 or 1. I just divided both sides by 2 there. I suppose that's extra, but probably worthwhile to put that. And then you solve that equation. Cosine is equal to 0 for pi over 2 and 3 pi over 2. You might have written plus 2 pi n or something like that, and if you did, I couldn't blame you because I actually didn't read on this screencast that this is one of those interval questions. So we're actually going to identify the 2 places between 0 and 2 pi. Hello to Kamel there. Between 0 and 2 pi, where we actually do have 0 for our x-coordinate, and those occur at pi over 2 and 3 pi over 2. So we'll leave those on there for now. I'll do the check in a second. And then over on the right branch, we're still with the cosine function. I guess I left something out there before. If we have ones or negative ones or zeros with the cosine function, same goes for the sine function, cos and sine. We're going to be going to those ordered pairs. These are quadrantal solutions. In this case, pi is the location between 0 and 2 pi when the x coordinate is negative on the unit circle. As it says in that textbook cutout that I got there, we have to check our solutions. It's not necessarily the case that all of those is valid, or frankly any of them, but you're going to be pretty confident that at least one of them is. But the idea is that we've squared, right? And so you have taken an equation which was not a quadratic equation, and you have changed it into a quadratic equations, and the properties of those functions are different, the property of the equations are different, and so you have to go check. And as you can see with my check, one of the solutions is actually invalid. It's the 3 pi over 2 solution that is invalid. You are going to need to know how to perform trigonometry to do the check, obviously. It's a little bit more than just some basic arithmetic. So you would go through and you go, okay, I'm checking this time with the original equation. Absolutely, for sure, go back to the original equation. I take the first solution, so pi over 2, the cos of pi over 2 is 0. Add 1, that's the left-hand side, that of course equals 1. And then you'd have to know that the sine of pi over 2, which is 90 degrees, that's also 1. That's the y-coordinate at 90 degrees. So that solution checks out because the left side and the right side are equal to each other, sorry. This is where this 3 pi over 2 fails, because cos of 3 pi over 2 is 0, that is true. So 0 plus 1 does make 1, so that's the same. Check out, the same thing is happening on the left side of the equation, but on the right side of the equation, of course, we all know the sine of 3 pi over 2 is not the same as the sine of pi over 2. The sine of 3 pi over 2 is the y-coordinate at 3 pi over 2, which is negative 1, so that's why that solution is no good. And for trigonometry reasons, you can understand why pi works. Cos pi is negative 1. If you add 1 to that, you get to 0. And the sine of pi, that's the y-coordinate at pi radians. The y-coordinate is 0 because it's on the x-axis. That's a hard question. I would definitely do that again, all by yourself, because as I said there before, actually, there's a conceptual leap at every single step. That's a tough one. The next example, or examples plural, I think I've only got one here. It's a multiple angles one. This, again, into the challenging realm because it tests your understanding of the general solution, and then what do we do if we have multiple angles, they call this. So when theta or t or u or x or whatever is in there, it's called in the argument of that ratio. We have to solve, and then we're going to have to make some adjustments. What you see here is a fairly basic equation, just the cosine of 3t. If that was equal to 1/2, what do we do? What is the situation? Well, cos 3t, we've learned about that. The period of cos 3t is 1/3 the length of cosine, right? So instead of having a period of 2 pi, it's 2 pi over 3. All right. This is the function cos 3 t, if you want to call it like that, or theta. And then this would be the line 1/2. And what we notice is there's a solution that pops up at pi over 9, and then there's a solution that pops up at 5 pi over 9. Neither of those is something that you would come up with in the unit circle. There's some mathy explanation up there from our textbook, but I'm going to show you here, I guess, in video form, how do we come up with these solutions? Okay, how do we get these ones? Okay, you can, just by my explanation, appreciate what's happening here. There's the default 2n pi that we've been talking about, and then we're going to divide it by 3. Yep, for sure, because there's a 3 in there, and 2n pi divide by 3. But you're going to have some instruction here about how do we get to these two guys. Okay? So, actually, this one is, what I just talked to you about is the ending of this equation, as you might be able to tell. It says solve that, and it is a general solution situation because it doesn't actually provide an interval. Thank goodness I read that this time. So here we go. Example 7, give that a shot. You're going to have to isolate it, spoiler alert or whatever, reverse alert. It isolates to exactly what I just showed you. Have a think about how you're going to get to the answer that I just talked about. And I'll come back just to cut down the time. Okay, away we go here. This is the easy part. Oh, sorry, the top part here. Isolate, as I said there and have said in the past. Add 1 to both sides, so you get 2 cos 3t. It's not cubed. That's cos 3t. That looks kind of messy. Okay, and then divide by 2, and you're at cos 3t equals a half. So that one, you pause there, and you've done some work isolating for that equation. Now, a strategy that I strenuously encourage you to bring on board here, the reality is that cos 3t has to equal a half. So we have to think about our unit circle, hey Noah, situation or our chart or whatever, but those things are not in terms of triple an angle. Those are just in terms of an angle. And so for the reason of maybe simplifying and also the reason for adding to your toolkit this substitution, which is actually going to be something that you get into in your calculus courses if you take them, is replacing. And we did this with factoring, and it's actually really, really important, I think, that you do it here. So the idea is you're going to introduce this u. So that's an expression that you're going to put into the cosine here, because then we can just use our ASTC in our chart like we know how to do. We do, for all intents and purposes, or maybe just to keep it a little more simple, we're just going to ignore temporarily the whole fact that it's 3 times the angle, and we're just going to go back and do this like we would have done a couple chapters ago. So now what you can do is you've got cosine of u is a half, and just solve for u, as I put over here in the strategy, just solve for u, the variable u over 0 to 2 pi like we would have done like I said a couple units ago, even a couple of examples ago. Okay, so what do? Well, it's positive 1/2. You know cosine is positive in the 4th quadrant and in the 1st quadrant, so that leads you to the chart or leads you to the unit circle, and there's my chart. I've just got the cosine row, and I've just got the relevant value that you need to use there. 2 solutions of u are pi over 3 and 5 pi over 3 for reasons that you should know how I got that. Pi over 3 is in the 1st quadrant. That literally is the reference angle. 5 pi over 3, I do 2 pi, and I take away the reference angle. That gets me to 5 pi over 3. Okay, so that is, you've got somewhere there. That's good. You've got the makings of the solution, but now you have to put your variable back in there. Again, this does come up, and then those people are going to take Calc AB. You're going to have to do this at some stage. So you might as well start getting used to it now as you do the trigonometry work in terms of that u, and now let's put our variable back together. Everybody that's in pre-calc and not ever going to take calculus, this is going to be good for your pre-calc. You set up an equation like I did here. 3t is equal to pi over 3. There's my pi over 3. And then we can put the 2n pi in there. This is a general solution type of deal, right? So we have the 2n pi, and we know where that comes from. And then what's nice and tidy here is that then you can just divide by 3. Okay, and that leads you to the pi over 9 and the 2n pi over 3 that we saw on the other slide. Okay, and you can do that also in the case of 5 pi over 3. 5 pi over 3 plus 2n pi. What happens here is that it gives us that anchor point. You would otherwise never be able to come up with pi over 9, at least not in a very efficient way or a very let's see here, consistent way to come up with that, I think. And this not only just to come up with answers here in this course, but also building some algebra skills for the future. So taking it from the top, isolate your equation in a multiple angle type of situation. Just isolate for the expression like you usually do. Okay, don't touch that one. And critically, you can't divide that out earlier on for reasons we're not going to get into in that screencast, but you cannot divide by the 3 from the beginning. Right, again, this 3t is what's known as the argument of the cosine. It can't be divided out. Okay, so then what do we do? Well, introducing this other variable is probably the best strategy. In fact, it's definitely the best strategy for you at this time. And so take it on board and know how to do it. What do we do? Well, then this takes us back to the easier trig, and we can just use our unit circle or our chart and the understanding of the quadrants in which this is going to be positive, in this case, and equal to 1/2 pi over 3 and 5 pi over 3. Then reintroduce the variable, and then you can divide. Then you can divide out that 3. And what does that do? It gives us that anchor point, pi over 9, and then it introduces the actual period of the function that you were dealing with. In this case, it's 2 pi over 3 period. Okay, that gets me example 6 and example 7, so that's part 1 of this, and there's going to be another screencast for examples 8 and 9. Okay, good stuff with that.